Good evening. Today we will see how to solve one of the problems in the last year thermodynamic question paper. The question is like this. A mass of 15 kg of air in a piston cylinder device is heated from 25 to 95 by passing current through a resistance heater inside the cylinder. The pressure inside the cylinder is held constant at 300 kPa during the process and heat loss of 60 kg occurs. Determine the electric energy supplied in kilowatt hour. Whenever we get a question like this, it's better to draw a diagram indicating the system so that it is easy for us to understand what is happening. So this is the piston and the cylinder is drawn as a sketch. The 60 kilojoule is going outside of the system as a waste of energy, and the pressure is 300 kilopascal, and temperature at the initial stage 25 degrees Celsius, then it increases to 95 degrees Celsius. And we can also understand from here the pressure is held constant. So this is a constant pressure process. They have not mentioned anything about the volume, so we need to calculate it. We will come to that part. So before going to solve this, we need to understand one thing. So this is in line with the first law of the thermodynamics, whereas if you see that heat transferred is change in internal energy plus work done. So here that is the requirement that we have to give it to the electric coil so that the process happens. So here if you see that there is also a heat loss. So the electric energy required is change in internal energy plus work done plus heat loss to the surroundings. Because in the second law states that all the heat whatever we are giving that cannot be converted to 100% work. There is also change in the internal energy. So change in internal energy also there. So if you give all these three things, that is the requirement of the electric energy that we have to give to increase this temperature and the work to happen. So the change in internal energy is mcp delta t. So when you take 15 and cp of the air and delta t, we get 1055 kilojoule. Okay. The next is the heat loss to the surroundings. So that is directly mentioned. So volume is not directly mentioned. We have to find the volume. So we can use the ideal gas equation P1 V1 mR equal to mR T1. From that we can find what is V1 value, which is 4.27. That is the initial volume when the process starts. The next is V2. Using the same way, if you calculate the V2, you will get 5.28. Whenever you use this, be little careful to put it in the Kelvin. The temperature has to put it in the Kelvin. That's why 273 is added. So we can, when you take a V2 minus V1, you know what is the volume change. So we know what is work done, because all the work, all the heat, whatever we are giving, that is not converted to work. So we calculated the change in internal energy. Then work done is nothing but a PdV. Now from using this formula, we calculated what is the change in the volume. So when you calculate when you multiply that with pressure, you get the work done, which is 301 kilojoule. So electrical energy input is nothing but 1055 plus 301 plus 60, which is 1416 kilojoule. Now again it is asked what is the required unit in kilowatt hour. So this is in kilojoule. So what I am simply doing, I am multiplying it by hour and dividing by hour. So what happens now? Kilojoule hour divided by hour. Hour you can write it in a seconds. So I am writing it as a 3600 seconds to convert the kilojoule to kilowatt. So when you do that, you get 0.393 kilowatt hour. So this is the solution of the problem. So whenever you get this kind of a problem, first draw one free body diagram kind of thing. Based on that, and apply start applying the thermodynamic first and second laws, you will get the solution. Thank you.